Okay, Assalamualaikum warahmatullahi wabarakatuh. We're going to continue with a switch mode inverter. We have looked into the single phase half bridge inverter with resistive load. So again, this is a DC to AC. So if you think about the AC output in our EPO 510, we're going to have three main output waveform, which is the first one will be the square wave output, and then we have a quasi square wave output, and we have the third one is the SPWM output. So we have the bridge topology followed by three techniques, which mainly square wave output, quasi square waveform, and SPWM switching scheme control technique. And in terms of the circuits, we can have a half bridge inverter and also the full bridge inverter. Okay, so let's just recap on what we did on the last class, whereby we have a single phase half bridge inverter with a resistive load. So this is the circuit of a single phase half bridge inverter, whereby we only utilize one of the leg and we use the two switches here, S1 and S2, and the other legs we use the capacitor. So we assume that we have a very large capacitor, therefore the capacitor will be charged to half of the input voltage, and the C2 also will be half of the input voltage, right? So the circuit operates whereby whenever S1 is on, S2 must be off. So it works alternately, or anti-phase they call it. So you have to have S1 on and S2 is off. So whenever the top switch is on, the current will flow through this side and then come to the switch 1 and then go through the load and finally goes to the C2 and come back to the supply, right? So in that path, we're going to have the output voltage will be half of the 100 volt. Okay, it will be a positive voltage whenever S1 is on, and whenever S2 is on, the path of current will be through the C1 and then in reverse of the load go to the opposite of the load polarity and come to the C2 S2 and finally come back to the supply voltage. So in this case, you're going to have a negative voltage across your output, right? So for the square waveform, you're going to have a switch 1 will be on theoretically from 0 to 180 degree, but in PSIM, to avoid some problems, it is set to 1 to 179, but in theoretically should be 0 to 180 degree. For S2 will be on from 180 degree to 360 degree. Okay, all right, so now let's look at the waveform. So that will be your square output voltage. This is your output voltage, right? So this is your output voltage whenever S1 is on. This is S1 on, the top switch is on, you can be connected to the positive half of the should be half of the input voltage. Wherever S2 is on, okay, you're going to see maybe a negative voltage across the load. Okay, so it's square waveform. So when we look into the harmonics of the output voltage, you will get the familiar waveform as we did for the half wave for the square wave input current. So you're going to get Cn, which is equals to 4 IDC over n pi for the components, the amplitude of the currents here, right? And the harmonics are located at fundamental and all odd harmonics for square waveform. And then we proceed with the quasi square waveform. Okay? In order to produce the quasi square output, we're going to turn on switch 1 from 330 degree to 150 degree, and S2 will be turned on from 210 degree to 330 degree. Okay, so by doing that, you're going to obtain the quasi square output. So this is where S1 is turned on, and similarly for S2 you're going to get the negative voltage across your output resistor. So you have a quasi square waveform, quasi square output, and therefore when you look into the harmonics of the quasi square waveform, you're going to get this sort of harmonic spectrum. You have fundamental components, and we can calculate the amplitude of the components here by using 4 IDC of 4 the amplitude, which is half of the voltage, 4 multiplied by half of the input voltage, divided by n pi multiplied by cos n pi over 6, right? And we have a component and fundamental and odd harmonics, but no triplet harmonics. We don't have components at third, ninth, and the third or the triplet harmonics. Okay, by looking at, if you compare between quasi square waveform and square waveform, we can say that the magnitude of the fundamental is reduced, and the quasi square will have no triplet components compared to square as shown. Therefore, the above or the output waveform for quasi square waveform is better than the square waveform. And then we proceed with the SPWM switching scheme, whereby the first technique is by using the unipolar PWM. For unipolar PWM, we must have two comparators here, okay, whereby you're going to compare the sinusoidal modulating signal. This is a sinusoidal modulating signal, and then you compare with a triangular carrier signal. The carrier signal frequency, the carrier signal frequency here also will determine the frequency of the two switches here. Alright, so the two switches, the switching frequency for the two switches here depends on the frequency of the carrier signals. Right, so let's look at the waveform. Right, so we have also the modulation index parameter. So modulation index is defined by the ratio between the amplitude of the modulating signals divided by the amplitude of the carrier signals. That gives the value of modulation index. Right, so let's look at the waveform. Right, for unipolar PWM, the carrier signals consist only positive value. If you look at the waveforms, it only consists of the positive value of carrier signals. So the carrier signals is triangular, but it consists only 0 to 10 volts here, so it is a positive voltage. Positive voltage, and then you compare with the modulating signals. The sinusoidal modulating signals will be compared with the triangular carrier signals with a positive. So this is unipolar. The output, which is the green waveforms there, will be connected to the S1. So this will be connected to the S1, switching 1, the top switch. And for the other comparator, you're going to have a different modulating signals. Right, now the modulating signals is the opposite to the modulating signals for the first comparator. So you start with a negative half negative value, and then you have a positive half cycles. So you have negative half cycle, positive half cycle, compared to the first comparator, whereby it is a normal sinusoidal modulating signals. Right, therefore you will produce the green waveform, and this green waveform will be connected to S2. And then the same circuit operation. Whenever switch 1 on, your output will be connected to the positive voltage. Half bridge, there will be, therefore the amplitude will be half of the supply voltage. Whenever S2 is on, it will be connected to the negative voltage. Let's see here. So this is when S1 is on, and we have whenever S2 is on, you have a negative voltage, so it's positive. But for the unipolar PWM, you will see that at one time there is a negative or zero level, which means S1 and S2 simultaneously turn off. So in that case, output voltage will be zero. So the waveform will appear as in this waveform. So this is the waveform for unipolar PWM. Right? Okay. So now let's proceed. Before that, this is the Morrissey index, the definition of Morrissey index. So it is always the peak of the modulating signals divided by the peak of the carrier signals. And again, the carrier frequency will determine the switching frequency of the switches. Right. Then when we look into the harmonic spectrum of the PWM waveform, the output waveform, we're going to see that the characteristic of the harmonic spectrum for the unipolar PWM is as displayed in this waveform, harmonic spectrum, whereby you have a component at the fundamental. Right, so you have the component at the fundamental, right, 50 Hz, no low order harmonics. So if you look closely, there is no low order harmonics. Ignore that. It's probably a noise. There is no low order harmonics, which means we don't have third, fifth, seventh harmonics, but we have the harmonics around the switching frequency and its multiple. Yeah, so our switching frequency is 2 kHz. Therefore, there is a harmonics around the switching frequency, which is the side bands, and its multiple. So you have 2 kHz. Next will be 4 kHz, and then you can have 6 kHz, and the rest. So we have that side bands or the harmonics at this around the switching frequency. We don't have component at. There is no component at 2 kHz, no component at 4 kHz, but we have harmonics around switching frequency. So this is characteristic of the PWM, of the unipolar PWM output. And again, you can simply calculate the amplitude of the fundamental by using this equation, whereby the amplitude of the fundamental components equals to the Morrissey index multiplied by V in over 2, because this is half bridge. Right? This is a half bridge. So if you talk about later on, we will discuss on the full bridge, this will be changed to V in. Right? It will be changed to V in for full bridge. Okay, so now let's proceed with the next topic, which is on the full bridge. Right, so, but you can read this. The quality of waveform generated using SPWM is much better than the quasi-square output, where no low order harmonics of current present in the waveform as shown below. It is much easier to remove the high frequency component using small size of LC filter. I will show you the simulation how we can use the LC filter to remove the sidebands, to remove the high frequency components, and we let only the fundamental component to pass the filter. Therefore, the load will see only this fundamental component, and therefore we have an AC voltage output. Okay, so now let's proceed with the single phase full bridge inverter with resistive load. Okay, we start with a unipolar. Yeah, once you see two comparators, that will tell you this is comparator. Again, this full bridge inverter also can produce the square wave and quasi square wave form. It just we don't show here. You can also have the square wave output as well as the quasi square output. You can have both to the full bridge as well. And for the full bridge, you must know that these the diagonal switches. In this case, that switch and that switch is known as the diagonal switches. They will be triggered instantaneously. They will be triggered simultaneously, and the other switches, which is switches, the other diagonal switches will be having the same pulse or same control signals. So this is the arrangement for the full bridge. Again, whenever let's say we have let's label let's label this as a T1, switch 1, then you have switch 2 here, then you have switch 3, as well as S4 there. Right? So if you look closely, the first comparator here will be connected to the S1, and the other one will be connected to S2. So both S1 and S2 will receive the signals from the first comparator here. Right? And the other two switches will receive the output signals they will receive the output or the PWM signals from the next the comparator. So that will be S3 and S4. So the circuit operation is that whenever S1 and S2 is on, the current will flow through S1 and then goes to the load R, and then flows through S2 and finally come back to the supply voltage. So in that case, we see this is short circuit, that also will be short circuit. So the voltage across the load will be equals to the input voltage. So whatever the value of V in will be also impressed across the load RL here. So this is your RL, the voltage across your load here. So this is again, this we start with a unipolar PWM, right? So again, modulation index equals to V peak of modulating signals divided by V peak of the carrier signals. And now we're going to discuss two types of PWM, SPWM control. The first one, unipolar, we have discussed it just now, unipolar PWM, whereby you need to have two comparators, and then the modulating signals of the second comparator will be the inverting version or the mirror image of the first modulating signal. Right? That is for unipolar PWM. So in this case, redo again. So you have unipolar PWM there. So we have V in equals to 100 volt. The modulation index 0.8, and we have a switching frequency of 1 kilohertz. So this is the two signals to the S1, S2, the diagonal switches, and the other diagonal switches will be receiving this the output of the second comparator. And this is your pulse SPWM1, pulse SPWM2, and finally this is the load voltage across the resistor. So you have whenever switch 1 on, will be connected to the positive voltage V in. Because it's a full bridge, therefore it is equals to V in. Right, this is definitely V in, and whenever S2 is on, it will be connected to minus V in. just that. So that will be the waveform. Again, we can calculate for, you can look at the harmonic spectrum. As I mentioned earlier, uh, there's a low order, there's a fundamental components, no low order harmonics, and finally number 3 is harmonic around switching frequency and its multiple. So here we have a 1 kilohertz as switching frequency, so therefore you have 1, 2, 3, 4, 5. So there are harmonics around the switching frequency and its multiple, and because this is a full bridge, therefore you multiply by V in instead of half of V in for the half bridge topology. Okay, now we proceed with the bipolar PWM. So for bipolar PWM, the first thing that you need to notice or aware of is that for bipolar PWM, we only requires one comparator. One comparator, a single comparator is used compared to the unipolar Pwm, whereby you need to have two comparator. So you have only one comparator, and the output of that, we'll just look at the output of the comparator. So the first, the original output comparator will be connected to, let's look at the waveform, S1, and the other one will be connected to S2, right? So that is the first output, and we have this inverter. Okay? So the output of this comparator, the inverting version of that will be connected, or the mirror image of that PWM will be connected to the other switches. Look at that. This is inverter. So you will be connected to the 1, 2, S3 as well as S4. Right? So you have one comparator, but the output of that will be separated. We have the output and also the inverting version of that output of the comparator will be used for the other diagonal switches. Right, so in this case, we're going to assume that we have, again, input voltage of 100 volt, and the modulation index is reduced to 0.8. So if you look at the waveform now, the amplitude of the modulating signal is slightly lower than the carrier signals. So for bipolar PWM, if you notice, if you look at the triangular carrier signals, it consists of positive and negative values. Okay, you have positive and negative values, and you compare this with the modulating signals, and this is the result of, because after you compare that, you must follow the rules of whenever Vm, whenever Vm greater than Vc, it will produce 1. The output of comparator will be 1, and whenever Vm lower than Vc, the output of comparator will be 0. Right? So in this case, you have, if you look closely, during that window, let's have a zoom it. Okay, so during that window, you can see that Vm is greater than Vc. So therefore, from that 0 degree to that particular degree, we have the output of 1. So whenever Vm lower than the Vc, you will produce a 0 PWM. Okay, so this is the, if you look closely, right, so this is the output of the comparator, and you have another the inverting version of the first PWM, which is that signals will be connected to the other switches here, which is to S4 and S3 at the bottom and the top. Right? So then if you want to know what is the voltage across the load, we just think of whenever S1 on, S2 is off, there will be a positive voltage across the load. Whenever S2 is on, S1 must off, and therefore across the load we will see a negative voltage. So therefore this will be your output voltage. Okay? So totally different with the unipolar PWM. So for bipolar PWM, you're going to see that the output, the load voltage consists only positive and negative. There is no zero levels. The voltage is not you cannot it doesn't stop at zero, so it jumps from positive voltage to negative voltage, positive negative voltage. So it's quite a high dVdt if you think of, right? So therefore this is the output voltage. It is from the sinusoidal signals that we expected, isn't it? We expect that we have a nice or ideal AC waveform, of course the sinusoidal signals, but in terms of PWM, bipolar PWM, we don't see at all any close to the sinusoidal signals. But the beauty is when we look into the harmonic spectrum, then we see that you have a components at the fundamental, okay, and then we have no low order harmonics, very similar to the unipolar PWM. So if you look closely, we don't see any voltage harmonics at the low order harmonics, but we have harmonics at the switching frequency and its multiple. So if you look closely, there is a harmonics at the switching frequency, at its frequency and its multiple. There is a word of odd multiple, sorry, there is a word of odd multiple, 1 3 5 multiplied by the frequency. So if you look at the spectrum, this is fundamental. This is fundamental component, and then there's no low order harmonics, harmonics at the switching frequency. So where is it? This one. Okay, so there is harmonics at the switching frequency. So our switching frequency is 1 kilohertz. Now you have a component at 1 kilohertz and its multiple, which means 1, 3, 5, 7, and the rest. You don't see frequency at 2 kilohertz, which is even multiple. Even. So you don't see component at even multiple, but it does only exist for odd multiple. 1, 3, so this is 3, component for 3, third harmonics, 3, 5, 7, the rest. Okay, clear? And again, if you want to measure the fundamental components, you only obtain this equation. V load, the amplitude of the fundamental component, equals to MA, the Morrissey index, depend on the Morrissey index. If you have 0.8, then you have a 0.8, and then the V in equals to the input voltage. Therefore 0.8, in this example you have 0.8 multiplied by 100, so you have 80 volt of the fundamentals, right? And the rest of the harmonics. So we're going to discuss on the detail of this harmonics when we talk about on the last topic on the PWM. Right, I hope you can easily understand that. So therefore, if you look closely, the frequency spectrum of bipolar PWM is quite similar to unipolar PWM. However, the magnitude of the harmonic component is larger than the fundamental. This technique has the advantage. However, the magnitude of the harmonic component is larger than the fundamental. So if you look closely, this is higher than the fundamental. And then the circuit also, this technique also has its disadvantages, whereby the output voltage jump from minus VD to VD, which means the device will experience a high dVdt voltage, the rate of change of the voltage. So this is dV over dt. Okay, so it jumps. If you look closely, it jumps from 100 volt straight to minus 100 volt, or from minus 100 volt to 100 volt. So each time there's a switching frequency period cycles, the device, the MOSFET transistor, will experience a large jump of voltage. So that will be also create some problems of a high divinity, because your switch will experience um, will experience a high voltage change, okay, compared to the unipolar PWM, whereby you have 0 and then positive voltage, and then 0 negative voltage, right? So this is basically the unipolar and bipolar PWM. And then you must memorize a characteristic of load voltage harmonic. You have to look into the disadvantages of using bipolar PWM. That's it. So now let's refer to, you can go to the my Padlet. I've already uploaded the PSIM, the circuit simulation for unipolar and bipolar PWM. So just compare, run the simulation, and reproduce the waveform. Reproduce these waveforms in the node, so that you can compare, you can understand easily. Right, so let's look at the this is a bipolar PWM, whereby you only have one comparator. And then if you look closely, this is actually to give a value, to vary the value, the amplitude of the modulation index. So you vary the amplitude of the modulating signals, and this determines the switching frequency. So here we have 2 kHz switching frequency, and then 2 kHz, and it operates with a 0.5 duty ratio. So it will on off, half of the cycle will be on, half of the cycle will be off. Right, so this is the circuit connection, the full bridge with a bipolar PWM. The modulation index 0.8, the switching frequency is 2 kHz. Okay, so if you run, then you can find, you can appreciate what it's all about. So if you run that, let's look at the sinusoidal signals, triangular carrier signals, and then we have SPWM generated. So this is your bipolar PWM waveform. I think I have to remove SPWM, okay, and add another screen with only SPWM. Alright, so this is the PSIM simulations of the bipolar PWM. So look at again, the triangular carrier signal consists of positive and negative voltage, but for the modulating signals you only have one single modulating signals. The amplitude of the modulating signals now will determine the switching modulating signal with the carrier signals. The amplitude of the modulating signals will determine the modulation index. Right? So if you vary the modulation index, you also vary the wave shape of the PWM waveform, isn't it? Yeah, so you can try that. Refer to the map Padlet. There are two PSIM circuits. One is a unipolar, the other one bipolar. So explore yourself. Look at the waveforms. And so this is the, and this will be the SPWM1, which is the switching signals. This is only a switching signals to the two switches, diagonal switches, which is S1 and S2. And if you invert that, if I add another screen here, the SPWM, SPWM2 will be the inverting version of the first comparator. The original output of the comparator. So whenever this is off, SPWM2 will be on. So it's opposite, and therefore if you look at the output voltage now, if if I can change that to can I see the wait, so VLoad, we also have this VLoad, right? So that is your output voltage. Can I remove this screen, delete the screen, right? So if you look further, whenever switch 1 is off, you're going to obtain the negative voltage. Whenever S2 or the other switch is on, and when the switch 1 is on, then the output will be connected to the positive voltage. So it's just a matter of positive, negative, positive, negative, positive, negative, right? So again, if you click this button FFT, I must remove the SPWM waveform signals, delete the screen, then I'm going to delete the screen as well. And now this is solely a load, right? Then you just hit this button, all right? So you hit this FFT button, then you can see, look at that. If you reduce this, so that is the switching frequency that you obtain, fundamental, and the amplitude of that will be, you can calculate the fundamental or component of the amplitude of the fundamental component using the M multiplied by V in. So our N is 0.8 multiplied by V in is 100, so you get almost 80 volts, right? But for the 80 volts here, but and there is no low order harmonics, low now order harmonics, but we only have a harmonics at switching frequency. So this is at switching frequency, at switching frequency. So there is no components at switching. Oh, sorry, there is harmonics at switching frequency and it's odd multiple. Okay, if you look at the next odd multiple, can I go to 7,000? There you are. So you have 2 kilohertz and 6 kilohertz during at the switching frequency and its multiple. You have the component odd multiple. But for the rest, we have the side bands. You have these side bands. All right, I think that's it for the unipolar and bipolar PWM. Next segment will be on the three-phase inverter, and finally we're going to continue with the detailed analysis of the PWM technique. So please download. I've already put in the website the Padlet, the PSIM circuit for unipolar and bipolar PWM. So you must explore. You also must need to memorize or recognize if you are given this sort of waveform for harmonic spectrum, you'll be able to tell that this actually comes from the bipolar PWM technique, right? And then if you see this waveform is exactly because of that, it is a unipolar PWM. So you have to differentiate. You look at the waveform, look at the what is the name for that waveforms, and this is important. Okay, right? I think that's it for the single phase inverter. We're going to continue with the three-phase inverter and detailed PWM. Thank you.